So continuing on the June 2017 exam, number 7, which figure has exactly 4 lines of reflection that map the figure onto itself? When we look at map the figure onto itself, what that means is, so you have something like this, a square, right? Map onto itself from a line of reflection. A little bit of confusion with this. Say this is A, B, C, and D, right? A, if we reflect over this line here, won't come back to itself. What it'll do is it'll land over here on B, but B will land on A. So the figure, if you check every point, it has a match on the other side of that line. Even though each point does not land back on the same exact location, each point has a match on the other side. So you won't have any new outline, so to speak, and that's kind of what we're looking at. So exactly 4 lines, though, is key here. A regular octagon will have 8. A rectangle will only have 2. An equilateral triangle will have 3. The square is going to have 4. You've got 1 straight up and down. Okay, you have 1 across and diagonally as well. So map onto itself, another word that I like to teach my students is think. When you see map onto itself or something like that, think symmetry. This is line symmetry. There's other problems that would have rotational symmetry involved. All right. So next, okay, key term here. So what we have is intersecting chords. The quick theorem that we're supposed to be using is, we call it product of the parts. Okay, so basically if you look at one chord, its 2 pieces multiplied together will equal the product of the other chord's pieces multiplied together. Okay, that's the shortcut. It's due to proportional sides and all that, but we can get into that, or you can ask me about that another time. So right now BC, DF bisects chord BC, and if BC is 12, bisect means equal parts. So we're going to take the 12 and turn it into 6 and 6. So that chord, the product of the parts of that chord is 6 times 6. Now FE is 5 more than DE. Well, I don't know what DE is, so call it X, and then EF will be 5 more. X times X plus 5. Now this is one of those cases where I'll show you the algebra, but the algebra actually makes the problem worse. So quick, let me just show you that. We should learn the mechanics. When you have a quadratic, we really should be trying to get 0 on one side. So let me just go through the mechanics of quadratic equations. Try to factor that. 9 and 4. That's what it would look like. Okay, x plus 9 times x minus 4 would produce this trinomial. Now we say either x plus 9 is 0 or x minus 4 is 0. The reason we have to get rid of this one is because we can't have a negative for a length. So x is 4 and EF, so DE is 4 and EF is 9. Now which one do they want? They want EF. Okay. The algebra kind of gets in the way. There actually was a much easier way to do this. Think back here when we had the 6 times 6. It's going to equal 2 numbers multiplied together. Right? So 36 is the product. It's going to equal 2 numbers multiplied together, and one number is 5 more than the other. Here's all you should be thinking, because essentially that's how I factored it. Think of numbers that multiply to 36. Okay, so you could use 1 and 36, 2 and 18. This is what's going on in my head here. 3 and 12, 4 and 9, 6 and 6. Now, which one of these combinations is 1 5 more than the other? It's the 4 and 9. EF is 5 more, so that's the one we wanted. So all this algebra is actually harder to learn than just use your brain. Okay, but there it is. All right, proof. You're given, let's mark the diagram based on the givens. So angle A is the same as angle EDF. Okay, so we've got congruent angles there. And AB, this side is the same as DE. Okay, maybe I'll pull those apart. Sometimes it can be a little tricky. Okay, so these are the same, and these are the same. Okay, which pair of corresponding parts and triangle congruency method would not prove the triangles congruent? Okay, that's interesting. All right, if we had AC the same as DF, AC, DF, that would be true by side angle side. Okay, which one's not? Let's get rid of that one. That one is. Okay. Okay, here's the problem. Okay, BC the same as EF would do this for us. Side-side angle is not a congruence theorem that we can use. And that's what this is. See, the angle that's congruent is not between the pairs of sides that are congruent. So it's technically, this is side-side angle. It's not side angle side. This is the one that's not true. Angle, angle, side, angle. We probably don't even have to test those because we've got that answer. All right, let's keep going. All right, divides proportionally. So DE divides AB and AC proportionally. Okay, so this is the side splitter theorem another way. When you divide the sides proportionally, we know that those are parallel. So, yeah, the proportional sides, that tells us those are parallel. Wow, this is going to be a lot. I see a lot going on in this problem. Okay, measure of angle. A is 82. Okay, I'm looking at right here. Since these lines are parallel, what we have here is really you have corresponding angles, right? So when the lines are parallel, corresponding angles should be congruent. So this position here would give you 26. We could figure this one out right now. Okay, so let's see if that's useful. So 82 plus 26, that's 108. 180 minus 108 is 72. Okay, so we're going to put 72 right here. Because you have another parallel, right? You're looking at this. That's 72 right there at D. And this one down here at B, that's going to give us 72 there as well. Now, we might not have needed that, but we could figure it out. Here's the key. This angle BDE. All right, let's isolate that. We've got B to D to E. All right, we know the top part of that's 72. So then 180 minus 72 is 108. And it's bisected. So 108 cut perfectly in half is going to give us 54 in each of these. Okay, so this is 54, this is 54. You know what? I'm going to use this one right here. Let's look at another aspect of this. All right, so you see we have these parallels, right? With a 54 right here, and what we're interested in is this angle. That's also going to be 54 due to alternate interior angles theorem. So it's 54. Wow, that's quite a bit going on in one problem. All right, number 11, which set of statements would describe a parallelogram that can always be classified as a rhombus? All right, now, this is that upgrade style of problem, you know, that we talked about in our classes quite a bit. We already have a parallelogram. Now, which would upgrade it to a rhombus or possibly even more? So if you have a parallelogram and you added a feature of diagonals perpendicular bisectors of each other, okay, So the diagonals have to bisect each other in a parallelogram. The fact that we add perpendicular as well is definitely a rhombus feature. Okay? If it was just a parallelogram, we would need this feature. To upgrade it to a rhombus to make these the same, you would need a right angle there. So that's true. Okay. Diagonals bisect the angles from which they're drawn. Again, since we have a parallelogram, if both diagonals do bisect their angles, that is an upgrade. Okay. So, just 1 and 3's out, just 2 and 3's out. Okay, it's one of these two. Diagonals form 4 congruent isosceles right triangles. Okay. Diagonals form 4 congruent triangles is true. That would make, all right, the 4 congruent triangles would make it a rhombus. Because of this going on, you get the right angles, those are the same. Yep. Okay, so that's definitely 4 congruent triangles that are right triangles. That's true. And they're, wait a minute. Diagonals form 4 congruent isosceles right triangles. Oh, they don't have to be isosceles to be a rhombus. Isosceles would make these the same. That doesn't have to happen to make it a rhombus. If it does, it still is. It's a square. Okay. Oh, but that's allowed too. I mean, technically a square is a rhombus, so yes, all of them. Yes, I could see the trick. So the trick, somebody that knows what they're doing might select one and say, well, wait a minute, that's a square. Yeah, but a square, the argument is yes, but a square is a rhombus. So technically it is choice 4. Okay, just double, yeah. Wow, tricky problem. Okay, so the equation of this circle. All right, there's a way now that my students have shown me there's a way to kind of cheat on the calculator and do it that way. I'm not going to teach you how to do this on the calculator. I'm going to teach you the math that I should. The math that I should teach is completing the square. Okay, we want to get this equation into center radius form. So we're going to use completing the square, and I'll show you some good math. If you know how to do it in your calculator, go ahead. All right, that is a test-taking tool. I got no problem with that. Okay, so there is no x term that's loose, so let's just leave x squared alone. What we're going to mess with a little bit is we're going to try to manipulate, the y part. Okay, so we're going to complete this square so that this extra y that's out here can get contained. I don't know what it's going to be yet. I'm going to leave the 20. I'm going to say equal to 0, right? And then, give me a second here. If I add something there, I'm going to add something over there. This number is what we're going to use right here. Whatever we put there is going to be used to complete the square. Okay, now these 3 terms will all come together to give us y minus 6 quantity squared. Negative 6 squared is 36. Okay. Leave the plus 20, that's 36. We'll subtract 20 from both sides. And what we have is, finally, center radius form. This tells us 0, 0, 6 is the center. Okay, it's the same numbers but opposite sign. And the radius, be careful here. It's always the square root of whatever's over there. Don't square it, take the square root of it. This is r squared over here. So you have to square root it to get r. So you have a center of 0, 6, radius of 4, it's choice 1. Good. A couple more for this. Actually, that takes us to the halfway for the part 1, so I'll stop at